Okay, so imagine like a master counterfeiter. They're trying to make fake cash, right? And then you've got this detective, super sharp, can spot a fake a mile away.
It's like that constant back and forth, right?
Exactly. The counterfeiter gets better, the detective's eye gets even sharper.
And what's so cool is that that's kind of what's happening with GANs. It's like, that's a pretty good way to think about it.
Generative adversarial networks.
Yeah, GANs, that whole idea, it's like this really elegant way to describe what's going on.
And the best part is we're not just like riffing here. We're diving straight into the source. This paper, Generative Adversarial Nets, back in 2014.
This is it. This is like the paper.
Ground zero for GANs. So before we get into all the adversarial stuff, paint me a picture here. What was so groundbreaking about AI that can, like, generate stuff? It almost sounds like we're trying to make AI into artists.
Yeah. For the longest time, AI was all about what they call discriminative tasks, like telling the difference between, I don't know, a cat and a dog in a photo.
Okay, classic image classification stuff.
Exactly. But generative models, this is different. It's like, how do you get AI to create that image of the cat from scratch?
From scratch. Okay, now that's wild. How do you even start to teach a computer to do that? Like, where do you even begin?
That's the thing, right? Older generative models, they had their limits, like trying to paint with a, I don't know, a blurry brush.
You get the idea, but it's not very precise.
Exactly. And the paper, it talks about these blurry distributions, which is basically just a fancy way of saying.
The way they were representing the data just wasn't cutting it.
Right. It couldn't capture all the detail, the nuance of the real thing.
So it's more than just spitting out random pixels. It's about, like, capturing the essence of something, those little details that make it look real.
Absolutely. And they were hitting these walls, using things like Markov chains, which is, it's like a step-by-step process.
Okay.
But it was slow, not very efficient, trying to, I don't know, draw a perfect circle, but you can only do it by, like, randomly placing dots on a page.
Painstaking.
Totally. You might get there eventually, but...
Yeah, I'm seeing why they were ready for a new approach.
For sure.
So, enter the generative adversarial network, the elegant solution to this blurry, inefficient mess.
And it is elegant.
So break it down for me. What's going on under the hood?
Okay, so 2 neural networks. So far, pretty standard AI stuff, right?
Yeah, I'm following.
But here's where it gets interesting. We have the generator. This is like our ambitious counterfeiter trying to create something, could be an image, a piece of music, whatever. But it has to be convincing. It has to look real.
Okay, so that's one side of the equation. What's the other?
The discriminator. Think of it as the detective, examining the generator's work with a fine-tooth comb, trying to spot the flaws, the tells.
So it's like a game, almost.
Exactly. A digital standoff.
I love that. So the generator is cranking out these fakes, and the discriminator is like, nope, I see right through you. But it's not just a one-and-done deal, is it?
Right. That feedback for the discriminator, that's the key. The generator takes that and learns from it.
So it's like, okay, I need to up my game if I'm going to fool this detective.
Yeah, cool.
Okay, that's cool. So we've got this back and forth, this adversarial relationship. That's where the magic happens. But what about the discriminator? How does it keep up? I mean, if the generator is constantly improving, doesn't the discriminator need to as well?
That's the beauty of it. It does. As the generator gets better at creating fakes, the discriminator has to get better at spotting them.
It's like a digital arms race.
A constant duel. And that back and forth, that's what makes GAN so powerful.
That's amazing. But I got to ask, how do you even begin to train a system like this? It sounds incredibly complex. So we've got this epic digital duel going on, but does it actually work?
That's the question, right?
Can you really teach a computer to become, like, a master forger?
Well, that's the beauty of this paper. They don't just talk about the theory, they actually show you the results. Like if you look at figure 1, it shows how the generator gets better over time.
Okay, let me pull that up. Figure 1. All right, so this is showing something called data distribution. Is that like the blueprint of the real thing? The thing we're trying to generate?
Yeah, exactly. It's like, think of it as like the essence of catness if you're trying to make pictures of cats, right?
Okay, I think I get it.
And what's really cool is, as the generator trains, you can see its output, the stuff it's making, it starts to look more and more like that real data distribution.
So it's like those blurry images we were talking about before.
Right.
They actually start to come into focus.
Exactly. It's almost like watching an artist, find their style.
I love that.
You start with like these rough sketches,
right,
and then over time,
it gets more refined.
Exactly. The lines get cleaner, the details get sharper, and then boom, you've got a masterpiece.
And the coolest part is they didn't just show us the pretty pictures.
Right, exactly.
They backed it up with the math, which...
Yeah, we'll spare you the equations. But basically what they showed was, mathematically, if you give these networks enough capacity to learn, the generator can actually, theoretically, perfectly replicate that real data distribution.
Whoa, okay, so they're not messing around.
Nope. They showed it visually, and they backed it up with equations.
Okay, I'm convinced, but I gotta see it to believe it, right? What about the actual images they generated? Show me the goods.
Ooh, I like where you're going with this. So, figures 2 and 3, that's where the fun begins. They trained Jans on all these different data sets, handwritten digits, faces, even scenes from CFAR 10.
CFAR 10, that's the one with, like, the cars and the...
Yeah, it's got all sorts of objects. Cars, planes, dogs, cats, the whole 9 yards.
I'm looking at these figures now, and I gotta say, for 2014, these are pretty impressive.
Oh, yeah.
But the paper did mention that back then, visualizing other generative models was, like, a whole different ballgame, right?
Yeah, it's true. Back then, you would usually just see, like, the averages.
The averages.
Like, what does the average face look like that this model has learned?
Interesting.
But here, with GANs, we're seeing the actual unique samples.
So it's like, you know that the Jan understands what a face is, but now it's actually generating individual faces.
Exactly, and that was huge.
Each with their own little quirks and everything?
Yeah, it was a whole new level of visual proof. And the thing is, they were very clear that this wasn't just about making pretty pictures.
Okay, now you've got my attention.
This was about something much bigger.
Spill the tea. What else can these GANs do?
Well, they talk about something called conditional generation. Imagine being able to give the Jan, like, a creative brief.
Like, make me a picture of a cat, but make it a fluffy cat and give it a hat.
Okay, maybe not with the hat in 2014,
Mm-hmm.
but you get the idea.
I do.
It's like you're giving the generator more guidance, telling it what to create.
So it's not just random anymore. It's like directed creativity.
Exactly. And that opened up a whole world of possibilities. But there's more.
Oh, there's always more.
The paper also hints at this other cool thing. The discriminator itself. It's not just a critic.
It's not.
It's actually learning some really useful stuff along the way.
What do you mean?
Think about it, right? To spot a fake, you have to become an expert on the real thing.
Makes sense.
So, in a way, the discriminator is becoming a connoisseur of data just by trying to spot the fakes.
That is so cool. So it's like a side effect of the whole adversarial thing.
Right. And what they realized was that those features, the things the discriminator is learning, they could be useful for other AI tasks.
So it's like the discriminator is picking up on these subtle patterns and using them for something completely different.
Exactly. And that was huge because it meant that Jans weren't just good for one thing.
They had all these other potential applications just waiting to be unlocked.
Exactly. It was like opening a treasure chest of AI possibilities. But, like with any good scientific breakthrough,
There's got to be a catch, right?
there's always a catch. Well, not a catch, but definitely some challenges they were still trying to figure out.
Yeah, no paper's perfect, right? So what kind of hurdles were they facing with Jans?
Well, one of the big ones was this idea of, like, training stability. Remember that back and forth we were talking about?
Right.
The generator and the discriminator. That delicate dance.
Yeah, the digital duel to the death.
Right. Sometimes that dance could get a little out of control. It's like, imagine if the generator just figured out a way to cheat the system.
Cheat. What do you mean?
Like, let's say you're trying to train a Jan to generate different fonts, right?
Okay, I'm following.
The generator, instead of learning to create all these different styles, it figures out, you know what? I can just generate, like, blurry versions of Helvetica.
Sneaky.
Right.
Yeah.
It's technically a new font.
It's checking the box, but not really getting the spirit of it.
Exactly. And the paper actually calls this out. They call it the Helvetica scenario.
I love that, the Helvetica scenario.
Because it highlights this issue where, yeah, the adversarial game is powerful, but you need that balance, that sweet spot where both sides are challenged.
But not so much that it breaks the whole thing.
Exactly. Otherwise, things can go off the rails.
So it's like trying to tune a really sensitive instrument or something.
Perfect analogy. And this whole challenge of, like, finding that right balance, making sure the training is stable, it really sparked a ton of research into different Jan architectures and training methods.
So it's like the paper opened up this whole new area of AI, and then everyone just rushed in to explore it.
Exactly. And that's what's so cool about looking back at these, like, foundational papers. You see the breakthrough, but you also see the seeds of everything that came after.
It wasn't the end, it was just the beginning.
Right. And they knew that, the authors. They were like, hey, we've got this cool thing, but there's still so much to figure out. It was like an open invitation to the AI community come on in, the water's fine.
And dive in. They did. I mean, it's amazing to think from this one paper, this idea of like two networks battling it out.
Crazy.
And now we have Jans that can do all this mind-blowing stuff.
Right.
Generate photorealistic images, compose music, even create those deep fakes that, make you question what's real anymore.
It's amazing how far it's come.
Yeah.
And it all started with this one elegant idea.
Exactly. It really is remarkable. So for anyone listening, if you want to check out the paper that started it all, search for Generative Adversarial Nets. Trust us, it's a wild ride. And that's our deep dive for today. Thanks for listening.